Have you ever stepped outside on a clear night, looked up at the stars, and felt that strange mix of awe and curiosity? That sense that there's something vast and mysterious just beyond your understanding. For centuries, humans have gazed into the cosmos and wondered, is all of this random, or could there be a deeper order hidden just beneath the surface? What if the universe isn't just a collection of unrelated phenomena, but a carefully structured masterpiece built upon principles we're only beginning to glimpse? Today, we're embarking on a journey to explore 22 compelling clues that point toward a hidden architecture beneath the cosmos. This isn't just about stargazing or imagining possibilities, it's about confronting evidence that suggests the universe operates according to a grand design. From the invisible grip of dark matter shaping galaxies to the inexplicable fine-tuning of the laws of physics, these clues hint at a cosmic blueprint far more sophisticated than anything we could have invented. By the end of this video, you won't just see the night sky the same way again. You'll understand why scientists and philosophers are increasingly open to the idea that there's a hidden order woven into the fabric of reality, one that connects the largest structures in the universe to the smallest particles, and maybe even to us. So settle in, open your mind, and get ready to see the cosmos in a whole new light. Think about gravity for a moment. The force that keeps your feet on the ground and the planets in their orbits is governed by a specific number, the gravitational constant. If that number were just a tiny bit stronger, stars would burn through their fuel too quickly, collapsing into black holes before life could ever emerge. If it were slightly weaker, matter would never have clumped together to form stars and galaxies in the first place. The universe would be a cold, dark, and eternal expanse of thinly spread gas. This isn't just a hypothetical scenario, it's a razor's edge of possibility, and our universe somehow landed on the exact value that allows for everything we see and experience. Now shift your focus to something even more fundamental, the strength that holds atoms together. The strong nuclear force is what binds protons and neutrons in an atom's nucleus, overcoming the powerful repulsion between positively charged protons. The precision here is staggering. If this force were a mere 5% stronger, hydrogen would be extremely rare in the universe, drastically altering the chemistry of stars and the availability of water. If it were slightly weaker, elements essential for life, like carbon and oxygen, might never have been forged in the hearts of stars. The very building blocks of planets and of our own bodies depend on this delicate and seemingly perfect balance. This phenomenon is known as the fine-tuning of the universe, and the list of these perfectly calibrated constants is long and profound. The mass of a neutron, the charge of an electron, the exact energy levels within a carbon atom, each one is set to a value that allows for complexity, chemistry, and ultimately consciousness. The odds of all these numbers aligning by random chance are astronomically small, so much so that it has led many physicists and cosmologists to question whether we are just incredibly lucky, or if there is something more purposeful at work. This isn't a new spiritual idea, it's a serious scientific puzzle. Sir Fred Hoyle, the astronomer who discovered how carbon is synthesized in stars, famously stated that the universe appears to be a put-up job, as if someone had been monkeying with the laws of physics. The evidence is so compelling that it has given rise to what is known as the Anthropic Principle, the observation that the universe we observe must be compatible with our existence as conscious observers. While some propose a multiverse, a vast collection of universes with different constants, and we simply inhabit the one that works, this only pushes the question back a step. What underlying architecture, what set of meta-laws, would allow for such a multiverse to exist and generate a universe like ours. The fine-tuning of physical constants remains the first and perhaps most powerful clue that we are not living in a random cosmos, but within a reality built upon a foundation of breathtakingly precise and seemingly intentional design. But the fine-tuning of physical constants isn't the only whisper of a grand design. To find our next clue, we have to rewind the cosmic clock almost all the way back to the very beginning, to a time when the universe was little more than a hot, dense soup of energy. The faint, cold glow that fills every corner of our sky today, known as the cosmic microwave background, is the ancient afterglow of that primordial fireball. For decades after its accidental discovery, it was thought to be remarkably uniform, a bland canvas of microwave static. But when we finally developed the technology to look closer, we discovered this canvas was not blank at all. It was covered in intricate brushstrokes. These subtle variations in temperature, these anisotropies, are like fossilized imprints of the universe's infancy. They are tiny, mere fractions of a degree, but they tell an enormous story. They are the seeds of everything we see today, the first gravitational whispers that would one day grow into the colossal walls of galaxy clusters and the vast, empty voids between them. What's truly astonishing is that these patterns are not chaotic or random. They follow a very specific, predictable kind of order that cosmologists call a scale-invariant spectrum. This means the patterns look statistically similar whether you're examining a large patch of the sky or a small one, a hallmark prediction of the theory of cosmic inflation. Inflation proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, smoothing out the cosmos and stretching quantum fluctuations from the subatomic scale to the cosmic scale. The fact that the patterns in the cosmic microwave background match this prediction so precisely suggests this explosive growth wasn't a violent, random event. It was a highly organized and controlled process, as if the universe were unfurling according to a specific set of instructions. This incredible alignment between theoretical prediction and observational evidence points toward a deep-seated order governing the birth of the cosmos. Furthermore, when we create sophisticated maps of the universe's large-scale structure today, tracing the positions of millions of galaxies, we find that this modern cosmic web aligns almost perfectly with the temperature fluctuations imprinted in that ancient light. It's as if the blueprint for the entire universe was encoded into its fabric at the moment of its creation. The faint patterns in the afterglow were the architectural drawings, and the galaxies and clusters we see now are the finished construction, built precisely to that spec. This undeniable connection between the infant universe and the mature cosmos we inhabit is a powerful argument that we are not just living in a universe, but within a structure, one that was carefully planned and executed from its very first moments. If the patterns in the cosmic microwave background are the ancient blueprints for our universe, then the large-scale structure we observe today is the fully constructed cathedral. For a long time, astronomers imagined galaxies as isolated islands in a vast, empty ocean of space. But as our maps of the cosmos grew more detailed, a breathtaking truth was revealed. Galaxies are not scattered randomly. They are organized into an immense, three-dimensional web of staggering complexity and beauty. This cosmic architecture consists of brilliant knots where galaxy clusters swarm together, connected by long, delicate filaments of star systems, all stretching across unimaginable voids of near-total emptiness that span hundreds of millions of light-years. This structure is so vast that it defies everyday comparison. If you could shrink our Milky Way galaxy down to the size of a grain of sand, the entire observable universe would be about the size of Earth. And on that planetary scale, the cosmic web would look less like a random sprinkling of sand and more like the intricate neural network of a brain or the root system of a colossal tree. It's a pattern that repeats itself at the largest scales we can measure, a fundamental organizational principle of matter in the universe. The presence of this immense, ordered framework strongly suggests that the cosmos is not a chaotic accident, but a construct that formed according to a specific set of rules. But what holds this magnificent web together, the gravity from the visible stars and gas we can see, is nowhere near powerful enough to sculpt matter on such a monumental scale. This is where the plot thickens, and we are introduced to the invisible architect of the cosmos, dark matter. We cannot see it, touch it, or directly detect it with any of our instruments, yet its gravitational influence is undeniable. It acts as the hidden scaffolding, the underlying framework upon which the visible universe is built. Think of it like this: if the cosmic web is a magnificent city of light, dark matter is the unseen foundation, the steel beams and concrete pylons buried deep underground that give the entire city its shape and stability. Our most powerful supercomputers run simulations of how the universe evolves, starting with the initial conditions seen in the cosmic microwave background. When they add only the known forces of gravity and the visible matter we understand, the simulations produce a bland, formless cosmos. But when they include the gravitational effects of dark matter, something incredible happens. The simulation begins to form a web, filaments, nodes, and vast empty voids that look exactly like the maps we've painstakingly created from telescope observations. This is a profound validation. The fact that we can input the laws of physics and the seeds from the early universe and reliably output the precise large-scale structure we see today indicates that this isn't random. It is the inevitable outcome of a universe built upon a specific and highly ordered architectural plan. Now, if the cosmic web is the grand cathedral of the universe, we have to ask, what is it made of? We can see the glittering galaxies, the shining stars, but they are merely the decorative lights on the surface. They are not the foundation. For that, we must turn to our fourth clue, the most enigmatic substance in the cosmos, dark matter. This is not some rare or exotic material. It is the universe's primary building block, making up roughly 27% of everything that exists. Yet it is utterly and completely invisible. It does not emit, absorb, or reflect any form of light or energy we have ever been able to detect. It is a ghost in the cosmic machine, and we only know it's there because of the undeniable gravitational hand it has on everything we can see. The first hint of this phantom presence came from the way galaxies spin. Our own Milky Way and every other spiral galaxy we observe rotates at such a tremendous speed that the gravity from all the visible stars and gas should not be nearly strong enough to hold it together. By all rights, these galaxies should have flung themselves apart eons ago, their stars scattered across the void. The fact that they haven't tells us there must be something more, a huge amount of invisible mass whose gravity creates a powerful gravitational glue, holding the entire structure together. This unseen matter forms a vast spherical halo around each galaxy, far larger than the visible disk of stars we see, anchoring the entire system. But dark matter's role is far greater than just being a galactic anchor. It is the master architect of the large-scale structure itself. Remember those delicate anisotropies in the cosmic microwave background, the seeds of all structure. Those tiny ripples were primarily in the dark matter. After the Big Bang, as the universe expanded and cooled, dark matter, unaffected by the intense radiation pressure that buffeted normal matter, began to clump together first. It collapsed under its own gravity, forming a hidden scaffolding, a cosmic skeleton. Then, much later, the ordinary atoms. The stuff that makes up you, me, and every star were drawn by gravity into these pre-existing wells of dark matter. The galaxies and clusters we see today didn't just form anywhere, they formed precisely where the dark matter had already laid down the framework. This is why the behavior of dark matter is so crucial to the idea of a hidden architecture. It doesn't just exert gravity randomly, it seems to follow very specific, predictable rules. It clusters in a particular way, it forms halos of a certain shape, and it interacts with itself and with normal matter in a manner that is both consistent and structured. The fact that we can input these rules into a supercomputer simulation and accurately reproduce the entire cosmic web we observe is astounding evidence that we are dealing with a fundamental component of the universe's design, not a chaotic anomaly. It behaves like a hidden set of instructions, a built-in code that guides the construction of the visible cosmos. The profound mystery, of course, is that after decades of searching with our most sensitive detectors buried deep underground and pointed at the skies, we still have not directly caught a single particle of dark matter. We see its shadow everywhere, we feel its gravitational pull, we have mapped its distribution across the universe, but its true nature remains one of physics' greatest unsolved puzzles. This very elusiveness is itself a clue. It suggests that the architecture of the cosmos operates on a level that is fundamentally different from the ordinary matter we are made of. It is a hidden framework, the beams behind the walls and the foundations under the floor, absolutely essential for the stability of the entire structure, yet designed to remain out of sight, waiting for us to discover the tools to finally reveal it. Just when we thought we had a handle on the universe's structure, held together by the invisible hand of dark matter, an even more baffling discovery turned our understanding on its head. For most of the 20th century, astronomers believed the expansion of the universe, the aftermath of the Big Bang, was gradually slowing down. The collective gravitational pull of all the galaxies, they reasoned, was acting like a cosmic brake, gently tugging on the fabric of spacetime and decelerating the great outward rush. Then, in the late 1990s, two independent teams of researchers made a shocking observation. By measuring the distances to extremely far-off supernova, they weren't just looking back in time, they were effectively measuring the expansion rate of the universe throughout its history. To their utter astonishment, they found that the expansion wasn't slowing down at all. It was speeding up. The universe wasn't just expanding, it was accelerating. Something was actively pushing galaxies apart, and we had no idea what. This mysterious something was given a name that perfectly captures our profound ignorance: dark energy. It is now thought to be the dominant component of the universe, making up a staggering 68% of everything that exists. Unlike dark matter, which pulls things together through gravity, dark energy appears to be a property of empty space itself that generates a repulsive force, a kind of anti-gravity that pushes the universe apart. And its effect is not subtle. Every day, as the cosmos expands, the amount of empty space increases, which in turn creates more dark energy, leading to even faster expansion. It is a self-reinforcing process that, if it continues, points toward a future where distant galaxies will accelerate away from us so quickly that their light will never be able to reach us, leaving our descendants in a lonely, isolated island universe. The fine-tuning of dark energy is perhaps the most mind-boggling of all. The measured value of its strength is incredibly, inexplicably small, but if it were even slightly different, the consequences would be catastrophic. If dark energy were significantly stronger, its repulsive force would have overwhelmed the universe in its infancy. The delicate gravitational dance that allowed matter to coalesce into the first stars and galaxies would have been instantly shut down. The universe would have been ripped apart before any structure could form, resulting in a forever empty, frigid, and lifeless void. On the other hand, if dark energy were even a little bit weaker, its effect would have been completely negligible. Gravity would have won the day, causing the universe to slow its expansion, reverse course, and collapse back in on itself in a big crunch, long before life had any chance to emerge. We exist in a breathtakingly narrow window where the strength of dark energy is precisely calibrated to allow for both the formation of complex structures and the continued expansion necessary for a long-lived universe. This perfect balance is what makes dark energy such a powerful clue for a hidden architecture. It behaves less like a random substance and more like a built-in regulatory mechanism, a fundamental feature of spacetime itself that is set to a very specific value to ensure the structural integrity and longevity of the entire cosmic edifice. The most popular theoretical candidate for dark energy is the cosmological constant, an energy density inherent to the vacuum of space, first proposed and then later rejected by Einstein. The fact that this energy is uniform across the entire observable universe, affecting every region of space in exactly the same way, suggests it is not a local anomaly but a universal property, woven into the very fabric of reality. It acts like a cosmic thermostat, set to exactly the right value to allow the universe to build itself over billions of years, creating the conditions for galaxies, stars, planets, and ultimately, for us to look up and wonder at the mysterious force that makes it all possible. While dark energy reveals a force acting on the grandest scales, our sixth clue invites us to look at a completely different kind of evidence, one that is not written in the distribution of matter or the expansion of space, but in the very language of reality itself. This language is mathematics. Consider the simple, graceful arc of a planet orbiting a star. It doesn't wander randomly. It follows a precise elliptical path described perfectly by a mathematical equation formulated by Johannes Kepler centuries ago. Isaac Newton then showed that this motion and the fall of an apple here on Earth were both governed by the same universal law of gravitation, a mathematical expression of breathtaking simplicity and power. This was our first great hint that the cosmos might be speaking in numbers. This pattern of mathematical order isn't confined to the large and slow. Dive into the bizarre, counterintuitive world of the quantum, and you find the same thing. The behavior of electrons and photons, which seems so probabilistic and strange, is nevertheless described with incredible accuracy by the complex equations of quantum mechanics. The entire standard model of particle physics, which catalogues the fundamental building blocks of matter and the forces that govern them, is a mathematical structure. It's a framework of such precision that it can predict the outcome of experiments to more than 10 decimal places. This isn't just a useful tool, it's a stunningly accurate description of how nature actually works at its most fundamental level. The physicist Eugene Wigner famously wrestled with this in his essay, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He pointed out that mathematical concepts, which are often developed by mathematicians purely as abstract games of the mind with no thought for the physical world, turn out again and again to provide the perfect keys to unlock the universe's deepest secrets. It's as if a novelist writing a story purely from their imagination accidentally composed a text that contained the exact blueprints for a complex machine that actually exists. This goes far beyond utility. It suggests a deep, pre-existing harmony between the human mind's capacity for abstract reasoning and the operational logic of the cosmos. We are not imposing math on the universe. We are discovering that the universe is already, and always has been, mathematical to its core. This points directly toward a hidden architecture. If the universe is fundamentally mathematical, then its structure isn't just described by math, it is math. The laws of physics are not like laws passed by a government. They are more like the inevitable properties of a geometric shape or a numerical system. A triangle, by its very definition, has angles that always add up to 180 degrees. In the same way, our universe, by its very mathematical nature, might necessarily produce forces like gravity and electromagnetism, particles like electrons and quarks, and constants that have the specific values they do. The cosmos begins to look less like a physical object and more like a magnificent, dynamic equation solving itself across space and time. This perspective forces a profound philosophical question. Are we discovering these mathematical laws, or are we uncovering the inventions of a deeper cosmic mind? Is mathematics a human creation, a language we built that just happens to fit the universe remarkably well? Or is it something we perceive, a fundamental aspect of an objective reality that exists independently of us? The sheer elegance, consistency, and power of these mathematical principles, from the simplicity of Einstein's E equals mc squared to the complex symmetries of string theory, feel less like happy accidents and more like features of a grand design. They are the immutable rules of the game, the underlying code that every particle and every force field must obey, suggesting a reality built not on chaos, but on a foundation of flawless numerical logic. Just when we think we understand the universe's rules, it reveals a trick that seems to break them all. We've explored the cosmic architecture on grand scales, from dark matter's scaffolding to dark energy's push, but now we must shrink our perspective down to the realm of the impossibly small. Here, in the quantum world, particles behave in ways that defy every intuition we've built from our experience of reality. And no phenomenon is more baffling or more suggestive of a deep hidden structure than quantum entanglement. Imagine you have a pair of magical dice. You take one die to the farthest galaxy, billions of light years away, and you keep the other here on Earth. The moment you roll the die on Earth and see it land on a 6, you instantly know, without any delay, that the die in that distant galaxy has also landed on a 6. This isn't just a prediction, it's a fundamental, instantaneous connection. This is the essence of quantum entanglement. It's a phenomenon where two particles become so deeply linked that they share a single, unified quantum state. Measure a property of one like its spin or polarization, and you immediately know the corresponding property of its partner, no matter how far apart they are. Albert Einstein was deeply troubled by this idea. He saw it as a violation of his own theory of relativity, which states that nothing, not even information, can travel faster than the speed of light. This instantaneous connection across any distance seemed to suggest that influence could be communicated faster than light, a notion he famously derided as spooky action at a distance. For decades, physicists debated whether this was a real phenomenon or just a flaw in our understanding. Then, in the 1960s, physicist John Bell devised a mathematical test, now known as Bell's theorem, which could experimentally determine whether this spooky action was real or not. When the experiments were finally conducted with the required precision, the results were unequivocal. Einstein was wrong. The spooky action was real. This forces us to confront a staggering implication about the nature of reality. This instantaneous connection suggests that space, the vast emptiness that separates stars and galaxies, might be an illusion when it comes to the underlying quantum reality. Two entangled particles do not seem to communicate across space. Instead, their connection appears to operate outside of it, as if the space between them is not a barrier but is, in some fundamental way, irrelevant. It implies that what we perceive as separate locations might be deeply connected at a level beneath spacetime, woven together into a unified whole. This concept of non-locality, that objects can be instantaneously connected without being in the same location, is a direct challenge to our classical billiard ball view of the universe. It paints a picture of a cosmos that is not a collection of isolated points but an intricate, deeply interwoven network. The universe begins to look less like a vast emptiness dotted with isolated objects and more like a cosmic web of information, where every part is in silent, instantaneous communication with every other part. This hidden connectivity is a powerful architectural feature, a built-in wiring diagram that operates behind the scenes of our perceived reality. The consistency of this behavior is what makes it such a compelling clue. Quantum entanglement isn't a rare or fragile event that only occurs in exotic laboratory conditions. It happens all the time. It's a fundamental part of how particles interact and how the universe operates at its most basic level. This isn't a bug in the system, it's a feature. The fact that this bizarre, non-local connection is a universal and reliable phenomenon suggests it is part of the foundational code of the cosmos. It's a rule that particles follow, a rule that hints at a layer of reality where the very concepts of here and there lose their meaning. Some theorists propose that this points to a holographic universe, where our three-dimensional reality is a projection from a two-dimensional surface where information is stored and everything is connected. Others see it as evidence for a deeper, geometric structure to spacetime that we have not yet mathematically described, a substructure where these quantum links are as fundamental as the fabric of space itself. Whatever the ultimate explanation, quantum entanglement and non-locality stand as a profound testament to the idea that the universe is not what it appears to be on the surface. Beneath the illusion of separation and distance lies a hidden architecture of breathtaking connectivity, a cosmic design that binds every part of the universe together in a way we are only just beginning to comprehend. If the bizarre connectivity of quantum entanglement made the universe feel less like separate places and more like a single, interconnected entity, then our next clue takes that idea to its ultimate, mind-bending conclusion. It's a concept so radical that it challenges our most basic assumption about reality, that we live in a three-dimensional world. This is the holographic principle, and it proposes that everything we see and experience, every galaxy, every star, every person, every thought, might be nothing more than a projection, a cosmic illusion. To grasp this, think of an ordinary security hologram on a credit card. That shimmering, three-dimensional image of an eagle or a globe isn't actually inside the sticker. All the information needed to create a Chinese letter image is encoded on the two-dimensional surface of the holographic film. The 3D illusion emerges from the information stored on that flat sheet. Now take that concept and apply it to the entire universe. The holographic principle suggests that our seemingly vast, three-dimensional cosmos, with its incredible depth and volume, might actually be a projection of information stored on a distant, two-dimensional surface that surrounds us. This isn't just a poetic metaphor, it's a serious theoretical framework born from the study of black holes. Physicist Jacob Bekenstein and later Stephen Hawking discovered that a black hole's entropy, which is a measure of its information content, is not proportional to its volume as you might expect, but to the surface area of its event horizon. In other words, all the information about everything that ever fell into a black hole is somehow encoded on its two-dimensional boundary. This stunning realization led other physicists, like Gerard T. Hooft and Leonard Susskind, to propose that this might not be a special property of black holes, but a fundamental principle of the universe itself. Perhaps all the information within any given volume of space is encoded on its boundary. The implications of this are staggering. It would mean that the world we perceive, with its rich textures, immense depths, and solid objects, is a kind of magnificent illusion. The true reality, the fundamental architecture of the cosmos, would exist on a thin, distant shell where the laws of physics are simpler, perhaps written in the language of quantum information theory without the complication of gravity. Our 3D universe would be a holographic projection from that 2D surface, much like a video game is a complex, interactive illusion projected from the simple, binary code stored on a disk. This idea offers a tantalizing solution to one of the biggest problems in modern physics, unifying Einstein's theory of gravity, which describes the cosmos on large scales, with quantum mechanics, which describes the tiny world of particles. These two frameworks are famously incompatible, but in the holographic view, gravity in our three-dimensional world might not be a fundamental force at all. It could emerge from the quantum interactions happening on the lower dimensional boundary, just as the 3D image of the eagle emerges from the 2D patterns on the holographic sticker. Gravity, and perhaps even space-time itself, would be secondary phenomena, consequences of a deeper, information-based reality. This transforms our search for a hidden architecture. We are no longer just looking for hidden dimensions or unknown particles. We are potentially looking for the cosmic projector itself, the fundamental screen upon which the information of reality is written. The holographic principle suggests the universe is fundamentally computational or informational at its core. The laws of physics we are trying to decode might be the operating system for this cosmic projection, and we are living inside the simulation. This doesn't necessarily mean we're in an artificial simulation created by beings in another reality. It could mean that the universe is naturally holographic, that this informational structure is simply the way reality is built. While it may sound like science fiction, the holographic principle has generated testable predictions. Scientists have used it to solve complex problems in particle physics, and certain gravitational phenomena observed in the lab align with its models. The principle continues to gain traction because it elegantly solves profound theoretical puzzles, offering a coherent, if utterly strange, vision of a cosmos with a deeply hidden architecture, one where the richness of our three-dimensional experience is a magnificent shadow show cast from the edge of reality itself. Now, let's consider a feature of the cosmos so fundamental we often take it for granted. Yet it is perhaps one of the most powerful arguments for a hidden architecture, the unwavering uniformity of the laws of physics. Imagine if the rules of the game changed depending on where you were standing. What if gravity worked differently in the Andromeda galaxy, or the speed of light was faster in a distant star cluster? The universe would be a chaotic, incomprehensible mess, a cosmic casino where the odds are different at every table and no one knows the rules, but that is not what we see. Through our most powerful telescopes, we have scrutinized the light from galaxies billions of light years away. We analyze the spectral lines of their stars, the energy signatures of their gas clouds, and the violent eruptions of their supernova. In every single case, from the nearest star to the most distant quasar, we find the same atomic elements behaving in exactly the same way. The hydrogen atom in a galaxy 10 billion light-years away absorbs and emits light at precisely the same frequencies as a hydrogen atom in a laboratory on Earth. The nuclear fusion processes that power stars, the gravitational lensing of light around massive objects, the decay of radioactive elements. They all obey the same, unchanging set of rules, no matter where or when we look. This consistency isn't just spatial, it's also temporal. By looking at distant objects, we are effectively looking back in time. The light from those far-off galaxies has been traveling for billions of years, offering us a glimpse into the universe's youth. And even in that ancient light, we see the same physics at work. The laws governing the universe 13 billion years ago are identical to the laws governing it today. This is a profound revelation. It means the rules were set in stone, or more accurately, woven into the fabric of space-time from the very first moments after the Big Bang. They are not evolving or changing, they are fixed, stable, and universal. This global reliability is what makes science itself possible. It allows us to make predictions, to send probes to other planets with pinpoint accuracy, and to understand the life cycle of stars we will never visit. The trust we place in the consistency of physics is the bedrock of all discovery. If this uniformity were just a happy coincidence, a lucky alignment in our local cosmic neighborhood, it would be the most staggering coincidence of all. The odds against the same exact set of incredibly complex and specific laws arising independently and identically in every corner of a vast, expanding universe are astronomically, unimaginably small. This points irresistibly toward a deeper truth. These laws are not in the universe, they are of the universe. They are not local bylaws but a universal constitution, a foundational framework that was established as part of the cosmos's very architecture. This uniformity suggests a single, coherent source, a set of initial conditions or fundamental principles that applied everywhere simultaneously and consistently from the moment of creation onward. It is as if the universe was compiled from a single, flawless set of source code, and that program is running identically on every processor, in every galaxy, across all of time and space. This isn't just a clue to a hidden order, it is the direct evidence of the blueprint itself, written in a language of mathematics and physical constants that we are steadily learning to read. We find beauty in symmetry, a fact so deeply ingrained in our psychology that we are drawn to the balanced face, the perfectly formed snowflake, or the intricate pattern of a butterfly's wings. But this human appreciation for balance and order is not just a cultural preference. It appears to be a fundamental feature of the universe itself. Look up at a spiral galaxy, and you witness a stunning example of rotational symmetry, its arms swirling out from the center in a near-perfect logarithmic spiral. Look down through a microscope at a salt crystal, and you find its sodium and chlorine atoms arranged in a perfect, repeating cubic lattice. From the vast to the minute, symmetry is woven into the very fabric of reality, and this is far more than just a pleasant visual effect. It is a powerful, functional principle that governs the behavior of the cosmos. This love affair between physics and symmetry is not merely observational, it is deeply mathematical and lies at the very heart of our most successful theories. In the early 20th century, a brilliant mathematician named Noether made a discovery so profound that it fundamentally changed how physicists understand the universe. She proved a simple, elegant theorem. For every continuous symmetry in nature, there is a corresponding conservation law. This means that the beautiful patterns we observe are directly linked to the fundamental rules that keep the universe running. The fact that the laws of physics are the same everywhere, a symmetry of space, leads directly to the conservation of momentum. The fact that they are the same in every direction, rotational symmetry, gives us the conservation of angular momentum. The fact that they are the same at every moment in time gives us the conservation of energy, the very stability of our reality. The fact that energy cannot be created or destroyed and that momentum is always conserved is a direct consequence of these deep, underlying symmetries. The quest for symmetry reaches its apex in the Standard Model of particle physics, our current best map of the subatomic world. This entire theoretical framework is built upon a specific kind of abstract symmetry known as gauge symmetry. Think of it like this: the laws of physics remain unchanged even if we perform certain mathematical transformations on our description of particles and fields. It's as if you could change the color of every object in the universe according to a specific rule, and all the relationships between those objects, their attractions, repulsions, and interactions, would remain exactly the same. This requirement of symmetry is so powerful and restrictive that it actually dictates what kinds of particles can exist and what forces must mediate their interactions. The photon, the gluon, and the W and Z bosons, the carriers of the electromagnetic strong and weak forces, are not just random particles that happen to show up. They are required to exist by the demands of symmetry. They are the inevitable consequences of the universe's need to balance its books. But if symmetry is so perfect and powerful, why is our universe so interesting? A universe of perfect, unbroken symmetry would be a universe of bland uniformity, a featureless sea of energy where nothing ever happens. The magic, and perhaps the greatest clue to a hidden architecture, lies in what physicists call broken symmetry. Imagine a perfectly round, smooth ball balanced on the very tip of a sharp hill. This state has a high degree of symmetry. It looks the same from every angle. But it is also incredibly unstable. The slightest breath of wind will cause it to roll down into a valley below. In doing so, it has broken the original symmetry. It now has a specific location, an orientation, but it has also found a state of stable, complex existence. This is precisely what cosmologists believe happened in the very early universe. In the first moments after the Big Bang, all the fundamental forces of nature were unified into a single superforce, a state of perfect and elegant symmetry. But as the universe expanded and cooled, it underwent a series of phase transitions, much like steam condensing into water or water freezing into ice. With each transition, a symmetry was broken. The single unified force fractured into the four distinct forces we know today: gravity, electromagnetism, and the strong and weak nuclear forces. And with each broken symmetry, new properties emerged. The Higgs field, which gives particles their mass, is a prime example of a broken symmetry that allowed for the incredible diversity of matter we see. It is through this process of symmetry breaking that the simple, symmetric fireball of the Big Bang gave rise to the complex, structured, and wonderfully asymmetric universe of galaxies, planets, and people. This isn't a flaw in the design. It is the design itself, an architectural plan where complexity and structure unfold from simplicity through a carefully orchestrated process of breaking perfect symmetry. The universe values elegance not just in its balanced equations, but in its graceful, unfolding narrative from unity to diversity. For centuries, philosophers and scientists have wrestled with a peculiar and profound observation: the universe seems to know we are here. This isn't a statement of mysticism, but a recognition of an incredible series of coincidences. We've already explored the precise tuning of constants, the perfect balance of forces, the specific initial conditions of the Big Bang. The fact that we exist to notice these things is itself a powerful clue. This is the core of the Anthropic Principle, an idea that moves us from the how of the cosmos to the startling why of our own place within it. The principle comes in two main flavors, each offering a different perspective on this fine-tuning. The weak Anthropic Principle is almost a statement of logical necessity. It simply says that the universe must be compatible with the existence of observers because we are here to observe it. We could not possibly find ourselves in a universe that does not allow for carbon-based life, for planets, or for stars. So, when we measure the gravitational constant or the strength of the electromagnetic force and find them perfectly set for life, we shouldn't be surprised. In this view, it's a form of observational selection bias. We are the selectors, and we can only select a universe that allows us. It's like a puddle marveling at how perfectly the hole in the ground it occupies is shaped to fit its form, without considering that it was the hole that shaped the puddle all along. Then there is the strong anthropic principle, which takes a much more provocative stance. It suggests that the universe must necessarily have properties that allow life and consciousness to develop. This version implies a form of built-in directionality, a cosmic imperative that the universe should not just allow observers, but that it is in some way structured to produce them. This isn't just a tautology, it's a claim about the fundamental nature of reality. It hints that the emergence of conscious minds might be a key part of the universe's function, perhaps even its purpose. This moves us from a universe of chance to a universe that seems almost expectant, waiting for the conditions to be just right so that it can finally look back upon itself. Faced with the staggering improbability of our existence, many physicists have turned to the multiverse hypothesis as a way to explain the fine-tuning without invoking design. The idea is that our universe is just one bubble in a vast, perhaps infinite, cosmic foam of universes, each with its own random set of physical constants and laws. In most of these universes, the numbers are all wrong, stars never ignite, atoms never form, and life is impossible. But in a vanishingly small fraction of them, like ours, the dice rolled just right. We shouldn't be surprised to find ourselves in a universe that permits life, because we couldn't exist in any of the others. It's the ultimate expression of the weak anthropic principle on a grand scale. However, this multiverse solution, while elegant in its own way, doesn't actually eliminate the need for a hidden architecture. It simply shifts it to a higher level. For a multiverse to generate universes with varying constants, there must be a set of meta-laws that govern the process of universe generation itself. What mechanism allows for the creation of these bubbles? What principles dictate the range of possible constants? The multiverse doesn't explain fine-tuning away. It just trades the fine-tuning of this universe for the fine-tuning of a universe-generating mechanism. The question of a guiding framework is not answered, but merely relocated to a realm even more distant and difficult to probe. This brings us to the deepest implication of the anthropic principle, the question of cosmic intent. Does the universe have a purpose, or is our existence a magnificent but ultimately meaningless accident? The fine-tuning we observe feels intentional. It has the hallmarks of a system designed with a specific outcome in mind. The constants are not just within a life-permitting range, they are often set to values that maximize the potential for complexity. This goes beyond mere necessity and into the realm of optimization, which many argue is a signature of design. The anthropic principle, therefore, acts as a bridge between the hard data of physics and the profound questions of philosophy, challenging us to consider whether the cosmos is not just a place, but a project, one that has, against all odds, succeeded in becoming aware of itself. But all of these profound clues about the universe's structure lead us to a deeply personal and seemingly obvious question. Why does time feel like it only moves in one direction? We remember the past, we anticipate the future, and we are forever carried forward on an irreversible current from one moment to the next. This relentless, one-way flow is so ingrained in our experience that we call it the arrow of time. Yet, when we look at the fundamental laws of physics that govern the universe, from Newton's mechanics to Einstein's relativity to quantum theory, we find something astonishingly contradictory. These laws are almost entirely time-symmetric. They work perfectly well whether time is running forward or backward. There is nothing in the equation for gravity that says an apple must fall down from the tree. It could just as easily describe an apple leaping up from the ground and attaching itself to a branch. The equations governing the collision of two particles are equally valid if you reverse the film. At the most basic level of reality, the past and the future are seemingly equal and interchangeable. So why does our lived experience scream otherwise? The key to resolving this paradox lies in a concept from thermodynamics known as entropy, which is essentially a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of a closed system always increases over time. A hot cup of coffee will always cool down to room temperature, its heat dissipating into the environment. It will never spontaneously draw heat from the air to make itself hotter. A drop of ink in a glass of water will always spread out until the entire glass is a uniform light blue. It will never suddenly recoalesce into a single, dense droplet. These processes are irreversible, and it is this relentless increase in entropy that gives us a powerful, statistical arrow of time. We can remember the past because it was a state of lower entropy, and we can't remember the future because it will be a state of higher entropy. Our brains themselves are biological systems processing information in a way that is deeply tied to this increase in disorder, but this only pushes the mystery back a step. Why was the entropy of the early universe so incredibly low? To understand just how special this was, imagine a brand new deck of cards, perfectly ordered by suit and number. This is a state of very low entropy. Now, if you shuffle that deck, you dramatically increase its entropy, its randomness. The universe we see today is like a thoroughly shuffled deck, a complex, high-entropy mix of stars, gas, and radiation. But to understand the arrow of time, we have to ask about the initial conditions. Why did the universe start out as a new deck in a state of exquisitely low entropy? The Big Bang wasn't a chaotic explosion in the way we typically imagine it. It was an event of breathtaking order and uniformity. The early universe was a hot, dense, and incredibly smooth soup of particles, a state of remarkably low entropy that was poised to unfold and mix for billions of years. This initial condition acts like a cosmic wound-up spring. The universe was set with this immense potential, and the increase of entropy is the slow, inevitable unwinding of that spring. This unwinding is what drives all the processes that make the universe interesting. It powers stars, fuels life, and allows for the formation of complex structures like galaxies and brains. Without this low entropy starting point, the universe would have been born in a state of maximum disorder, a featureless, high-entropy chaos where nothing ever happens, and the arrow of time would be meaningless because there would be no change to give it direction. This presents us with our 12th clue, the fact that the fundamental laws of physics are blind to the direction of time, yet our universe possesses such a strong and undeniable arrow, suggests that the flow of time is not a fundamental property but an emergent one. It emerges from the specific, highly unusual initial conditions of our cosmos. The direction of time is not written into the laws of motion for individual particles. It is written into the grand architectural blueprint of the entire universe at its moment of creation. The low-entropy Big Bang is not just a fact. It is a profound feature that had to be specifically set for the cosmos to have a history, a future, and the capacity for complexity. This forces us to consider an incredible possibility, that the arrow of time is a fundamental part of the universe's hidden architecture, a built-in feature designed to allow for narrative, for growth, and for the emergence of conscious observers who can witness the magnificent unfolding of cosmic history. It suggests that time itself may be structured, not as a blank canvas, but as a carefully prepared stage upon which the drama of the universe can play out. The mystery of why time has a direction is therefore not just a puzzle of physics. it is a clue that the very fabric of reality was architected from the beginning to facilitate a journey from simplicity to complexity, from order to disorder, and ultimately from a silent beginning to a story yet to be fully told. As we've explored the grand architectural principles of the cosmos, from the arrow of time to the fine-tuning of constants, a pattern begins to emerge, one that suggests the universe might not just be described by mathematics, but might actually be mathematics in a very literal sense. This brings us to our 13th clue, which lies not in distant galaxies or subatomic particles, but in the abstract realm of numbers themselves. Throughout human history, certain mathematical constants and sequences have appeared with such persistent regularity in both nature and art that they feel less like human inventions and more like universal discoveries, as if we are slowly uncovering a numerical code woven into the fabric of reality. Perhaps the most famous of these is the golden ratio, often denoted by the Greek letter phi, approximately equal to 1.618. This irrational number possesses unique mathematical properties and appears with uncanny frequency in the natural world. Look at the spiral of a nautilus shell or the arrangement of seeds in a sunflower head, and you will find their growth follows a pattern that perfectly aligns with the golden ratio. This isn't just a biological curiosity, it's a pattern of optimal efficiency, allowing for the tightest packing and most effective growth. Now cast your gaze upward to the heavens. Many spiral galaxies, including our own Milky Way, exhibit spiral arms that unfurl according to a logarithmic spiral, a shape whose growth factor is governed by none other than the golden ratio. It's as if the same architectural blueprint for a seashell has been scaled up by billions to design an entire galaxy. Then there is pi, the ratio of a circle's circumference to its diameter. This transcendental number, beginning with 3.14159 and continuing infinitely without repetition, shows up in places that have nothing to do with circles. It is embedded in the fundamental equations of physics, from Heisenberg's uncertainty principle to Einstein's field equations of general relativity. The very geometry of the universe seems to be imprinted with this constant. The strength of the gravitational force between any two objects in the universe is calculated using pi, the probability equations in quantum mechanics that describe where an electron is likely to be found also rely on it. Pi seems to be a fundamental part of the universe's operating system, a key parameter in the cosmic code, but the numerical clues go even deeper. Some physicists and mathematicians have pointed to the mysterious role of prime numbers, those numbers divisible only by themselves and one. Primes are the atoms of arithmetic, the building blocks from which all other integers are constructed. While they seem to appear randomly within the number line, they also follow a deeper statistical order described by the Riemann hypothesis, one of the most famous unsolved problems in mathematics. Intriguingly, certain quantum physical systems, like the energy levels of complex nuclei, exhibit distributions that eerily mirror the pattern of prime numbers. This unexpected bridge between the most abstract pure mathematics and the behavior of the physical world suggests that primes might not be just a human mental construct, but could represent a fundamental, underlying structure to reality itself. This idea of a numerical underpinning leads to a breathtaking possibility that the universe might be computationally generated. If the cosmos is fundamentally mathematical, then it could be operating like a vast cosmic computer, running on algorithms where constants like pi and phi are fixed parameters and prime numbers are part of the processing logic. The laws of physics would be the software, and space-time and matter would be the output. This is not necessarily to say the universe is a simulation in the sense of being created by some advanced intelligence in another reality, but that its fundamental nature is informational and computational. The universe doesn't just use math, It is math in motion. The recurrence of these ratios and constants across wildly different scales from the quantum to the cosmic is what makes this such a powerful clue. It points to a deep, pre-established harmony, a coherence that transcends the individual components of the universe. It suggests that the architecture we are searching for is not made of bricks and mortar, but of numbers and equations, an elegant, immutable, and breathtakingly beautiful mathematical structure that has existed in a Platonic realm long before the Big Bang gave it physical form. We are not just living in a universe that can be described with mathematics. We are living inside a mathematical universe, and every spiral galaxy and every sunflower is quietly whispering the secrets of its code. Yet even in their terrifying simplicity, black holes are not lawless voids. They adhere to a set of remarkably precise and elegant physical laws that hint at a deeper order. The no-hair theorem, for instance, suggests that a black hole can be completely described by just three properties: its mass, its electric charge, and its spin. It doesn't matter if the black hole was formed from a collapsed star made of iron or one made of gold. All of that complex information about its original composition is, according to classical physics, seemingly lost forever. It's as if the black hole is a fundamental, purified object in the cosmos, stripped down to its most basic parameters, a perfect blank slate in the universe's ledger. This incredible simplification points toward a hidden layer of reality where complexity gives way to fundamental, clean mathematical truths. But the story of information took a dramatic turn with Stephen Hawking's revolutionary discovery. He realized that due to quantum effects occurring just outside the event horizon, black holes are not completely black. They slowly emit a faint glow of particles, now known as Hawking radiation. This process causes the black hole to gradually lose mass and, over unimaginable eons, evaporate completely. This raised a terrifying paradox. If the black hole evaporates, what happens to all the information about the stuff that fell in? The laws of quantum mechanics state that information cannot be destroyed, it must be preserved, but the classical view of a black hole annihilates it. This black hole information paradox represents a fundamental clash between our two most successful theories, general relativity and quantum mechanics, and suggests that our understanding of reality is profoundly incomplete. The most promising resolution to this paradox comes from the holographic principle, which we touched on earlier. The work of physicists like Leonard Susskind and Gerard T. Hooft suggests that all the information that falls into a black hole is not lost inside the singularity. Instead, it is perfectly encoded and preserved on the black hole's event horizon, the two-dimensional surface that surrounds it. The three-dimensional interior is a projection of that information. This means a black hole's immense volume can be described by information on its surface, making it a perfect natural hologram. This isn't just a nifty trick for black holes. It strongly implies that our entire three-dimensional universe might operate on the same principle, with its true information content stored on a distant two-dimensional boundary. Beyond their role as cosmic informaticians, black holes are also powerful architects on a galactic scale. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole, weighing millions or even billions of times more than our Sun. The gravitational ferocity of these monsters is not just destructive, it is also creative. As they devour gas and dust, they unleash titanic amounts of energy, heating the surrounding material and driving powerful jets of radiation and particles that can stretch for thousands of light years. This energetic feedback acts as a cosmic regulator, preventing too much gas from collapsing into stars too quickly. It effectively puts a governor on star formation, shaping the entire evolution of the galaxy that hosts it. The black hole and its galaxy are not separate entities. They are a co-evolved system, with the black hole acting as a hidden gravitational heart, pumping order and structure into the galactic body. This intricate relationship suggests that black holes are not cosmic accidents or mere dead ends. They appear to be integrated components of the universe's large-scale architecture, playing a vital role in the life cycle of galaxies. They are transformers of matter and energy, potential gateways to understanding quantum gravity, and living embodiments of the holographic nature of reality. Their very existence and their stubborn adherence to precise, discoverable laws, even as they break all others, point toward a cosmos built on a foundation of deep, consistent principles. To study a black hole is to study the universe's most extreme and honest laboratory, a place where the hidden architecture of spacetime is strained to its absolute limit, revealing its truest, most fundamental blueprints. When we picture the Big Bang, it's easy to imagine a violent, chaotic explosion, a storm of random energy erupting into being. But the more we learn about our cosmic origins, the clearer it becomes that this picture is profoundly wrong. The Big Bang was not an explosion of chaos. It was an event of breathtaking precision, a launch so perfectly calibrated that it seems less like a random accident and more like the ignition of a finely tuned engine. Everything that followed, every galaxy, every star, every planet, depended on the exquisitely specific initial conditions set in that first fleeting moment. Consider the most striking feature of the early universe, its overwhelming uniformity, the cosmic microwave background that fossilized light from the universe's infancy shows a cosmos that was almost perfectly smooth. The temperature across the entire observable universe varied by less than 1 part in 100,000. This is a level of consistency so incredible it would be like sanding a surface the size of the Earth until the highest mountains and deepest ocean trenches differed in height by no more than a few inches. This smoothness is absolutely vital. If the early universe had been even slightly more lumpy, with denser regions of matter, gravity would have quickly collapsed those regions into monstrous black holes, tearing the fabric of spacetime apart before stars could ever form. If it had been slightly smoother, matter would have been too evenly distributed, and gravity would never have been able to gather it into the first wisps of structure, leaving the universe a forever empty, featureless void. This perfectly smooth starting point is the ultimate low-entropy state we discussed earlier, the wound-up spring whose slow unwinding powers the arrow of time and all cosmic evolution. But how did it get that way? Why wasn't the beginning a chaotic, high-entropy mess? The leading scientific explanation is the theory of cosmic inflation. This theory proposes that in the first fraction of a second, the universe underwent a period of exponentially rapid expansion, inflating by a factor of trillions upon trillions of times in less than a blink of an eye. This incredible stretching would have smoothed out any initial wrinkles, much like inflating a crumpled balloon smooths out its surface, and would have also planted the tiny quantum fluctuations that eventually grew into galaxies. However, while inflation is a powerful explanatory tool, it doesn't actually solve the mystery of fine-tuning. It simply relocates it. For inflation to work as described, the hypothetical field that drove it, the inflated field, must itself have been initialized with incredibly precise properties. Its energy density, its interaction strength, and its rate of decay all had to be set to values so exact that invoking inflation to explain fine-tuning is like explaining a perfectly tuned watch by saying it was made by a perfectly tuned watchmaker. It pushes the question of initial conditions back one step, from the universe itself to the mechanism that gave birth to it. The need for such precise parameters within inflation theory itself suggests that we are dealing with a deeper, more fundamental level of order. This brings us to the heart of the clue, the specific initial conditions of the Big Bang, the perfect uniformity, the exact rate of expansion, the precise balance of energy and matter, feel less like a random roll of the dice and more like a preset configuration. It has the hallmarks of an architectural plan, a set of boundary conditions carefully chosen to guarantee a specific outcome, a long-lived, structured, and complex universe capable of giving rise to galaxies, stars, and conscious life. The universe wasn't just born, it was launched with a purpose-built set of instructions encoded into its very first moments. This undeniable fine-tuning at the beginning of time naturally forces a question that was once considered off-limits for science: what came before the Big Bang? If the cosmos started with such a specific configuration, could it have emerged from a prior state? Some theories, like the cyclic model, propose an endless sequence of universes, each ending in a big crunch that seeds the next Big Bang. Others, like the multiverse arising from eternal inflation, suggest our universe is one bubble in a vast, frothing cosmic foam where new universes are constantly budding off, each with its own random set of initial conditions. The most radical ideas, like those from loop quantum gravity, propose that the Big Bang was not a beginning at all, but a transition from a previous cosmic phase, a big bounce from a contracting universe. While these ideas are still speculative, they all point in the same direction. The initial conditions of our universe might be the product of a deeper, more fundamental reality. The architecture we are searching for may not have begun 13.8 billion years ago. Its foundations may be buried in the timeless laws of physics or meta-laws that govern the creation of reality itself. The flawless start of our cosmic story is perhaps the most compelling clue that we are part of something far grander, a reality built with intention, whose first chapter was written with such care that it ensured the story would have a chance to be told. Faced with the staggering improbability of our universe's perfect conditions, one of the most popular scientific responses is to propose that our cosmos is not unique. Imagine for a moment a vast, bubbling ocean of reality, where each bubble is a separate universe, each with its own randomly selected set of physical laws and constants. In most of these bubbles, the numbers are all wrong. Gravity is too weak, the nuclear force is too strong, and the universe either collapses instantly or flies apart into a thin, lifeless mist. But in a tiny, fortunate fraction of them, like ours, the dice landed just right. This is the essence of the Multiverse Hypothesis, an idea that attempts to explain our incredible luck by suggesting we simply won the cosmic lottery. This concept arises naturally from several leading theories in physics. The most prominent is eternal inflation, an extension of the inflation theory that gave us our smooth, early universe. In this model, the inflationary field doesn't shut off everywhere at once. Instead, in most regions it stops, forming a stable, pocket universe like our own. But in other regions, inflation continues eternally, constantly giving birth to new pocket universes, each with potentially different properties. Another version comes from string theory, which suggests there could be a staggering 10 to the 500 possible ways to compactify its extra dimensions, each configuration resulting in a different universe with different physics, a vast landscape of possible realities. On the surface, this seems to elegantly solve the puzzle of fine-tuning. There's no need for a designer or a pre-existing plan. With an infinite number of universes, every possible combination of constants will occur somewhere. We, of course, can only exist in one of the rare universes that permits observers, So our surprise at our own existence is a form of selection bias. It's the ultimate expression of the weak anthropic principle, offering a naturalistic explanation for why things seem so perfectly arranged for us. It turns a miracle into a statistical inevitability. However, this solution comes with a profound and often overlooked cost. The multiverse hypothesis doesn't actually eliminate the need for a hidden architecture. It simply relocates it to a higher, more abstract level. For this cosmic bubble bath to exist, there must be a mechanism, a set of meta-laws, that governs the process of universe generation itself. What are the rules of eternal inflation? What determines the properties of the inflationary field that allows it to spawn new universes? What defines the landscape of string theory and the probabilities of different vacuum states? The multiverse doesn't explain these meta-laws, it assumes them. This means we have traded the fine-tuning of this universe for the fine-tuning of a universe-generating mechanism. The same profound question of why these specific rules simply moves up one level. Why does the mechanism that creates multiverses have the precise properties that allow it to produce at least one life-permitting universe? If the meta-laws were different, perhaps no stable universes would form at all. The multiverse, therefore, is not an alternative to a cosmic architecture. It is evidence for an architecture operating on a truly trans-cosmic scale, a deeper framework that governs the entire ensemble of reality. This expansion of perspective is perhaps the hypothesis's greatest contribution. It forces us to think bigger. Our search for a hidden order is no longer confined to the space within our universe. We are now challenged to contemplate the possibility of a meta-reality, a realm of laws and principles that exist beyond the space-time of any single cosmos, a framework where the very concepts of before and outside take on new, almost unimaginable meanings. The multiverse doesn't simplify our quest, it magnifies it, turning our gaze from the architecture of a single building to the blueprint for an infinite city. If the universe is fundamentally mathematical, then what is it calculating? This question leads us to a clue that may be the most transformative of all, one that shifts our entire perspective on what reality is made of. We are used to thinking of the world in terms of matter and energy, the solid stuff of planets and stars, and the forces that move them. But a growing number of physicists are proposing that these are not the primary ingredients of reality. Instead, they might be secondary phenomena, emergent properties of something even more fundamental: information. Information theory, which began as a practical framework for communication engineers, has steadily expanded its reach into the deepest questions of physics. At its heart is the concept of the bit, a binary choice between a 1 and a 0, a yes or a no. This seems abstract and human-made, but what if bits are not just a tool we invented? What if they are the basic units of existence, the atoms of reality from which everything else is built? This is the radical proposition of the it from bit idea, suggesting that every particle, every force field, and every ripple in space-time is ultimately made of information. This perspective transforms our understanding of the laws of physics. Instead of being immutable rules written in some cosmic stone, they could be seen as algorithms, the operating software of the universe. Gravity wouldn't be a fundamental force pulling objects together, but a program that calculates the curvature of space-time based on the information about mass and energy within it. An electron wouldn't be a tiny speck of matter, but a stable, self-sustaining pattern of information processing. In this view, the entire cosmos is a vast, ongoing computation, and we are living inside the output. The strongest evidence for this incredible idea comes from one of the most extreme environments in the universe, the black hole. The black hole information paradox, which pits quantum mechanics against general relativity, creates a seemingly irreconcilable conflict over whether information can be destroyed. The most promising resolution, as we've seen, is the holographic principle, which states that all the information describing a three-dimensional volume of space can be encoded on its two-dimensional boundary. This isn't just a clever trick, it's a fundamental statement about the nature of reality. It suggests that information is not just in the universe is information. The three-dimensional world we experience is a projection, a holographic display generated from a deeper, two-dimensional layer of encoded data. This idea finds further support in the work of physicists like John Archibald Wheeler and his concept of the participatory universe, where observation plays a key role in bringing reality into existence. It also resonates with the field of digital physics, which explores models where the universe is literally a computational system, evolving step by step like a cellular automaton. While these ideas are speculative, they are grounded in serious mathematical physics and are attempts to grapple with the strange, informational nature of reality that our experiments keep hinting at. If this is true, then the hidden architecture we've been searching for is not made of unknown particles or hidden dimensions, but of bits and qubits. It is a computational architecture, a cosmic CPU running the ultimate simulation. This doesn't necessarily mean we are in a simulation created by some advanced intelligence. It could mean that the universe is naturally computational, that its most basic level of operation is the processing of information. The laws of physics would be the code, and the constants of nature would be the fixed parameters in that code. We are not just living in a universe that can be understood through information theory. We are living inside a universe that is an information theoretic system, a cosmic masterpiece of data and computation whose final output is the rich, complex, and conscious reality we experience every day. We have journeyed through clues written in the fabric of space-time, in the invisible pull of dark matter, and in the elegant language of mathematics. But now we arrive at perhaps the most intimate and profound clue of all, one that is not out there in the distant cosmos, but right here in the very experience of being. This is the mystery of consciousness, the simple, undeniable fact that it feels like something to be you reading these words, the soft glow of the screen, the weight of your body in the chair, the quiet hum of your own internal monologue. This rich, subjective experience is the one thing we know for certain exists, and yet it remains science's greatest unsolved puzzle. The conventional, materialist view holds that consciousness is an emergent property, a byproduct of the incredibly complex computation happening within the neural networks of our brains. According to this perspective, when you arrange matter in just the right way with 100 billion neurons firing in an intricate dance, consciousness simply happens, much like wetness emerges from the specific arrangement of water molecules. This seems logical, but it runs headlong into what philosopher David Chalmers termed the hard problem of consciousness. The hard problem isn't about how the brain correlates with experience. We can map which parts of the brain light up when you see the color red. The hard problem is why any of that physical processing should be accompanied by a subjective, inner experience of redness at all. Why aren't we all just philosophical zombies, sophisticated biological robots that process information and behave appropriately but have no inner light, no private movie playing inside? The sheer difficulty of explaining how subjective experience arises from objective matter has led a growing number of philosophers and scientists to consider a radically different possibility. What if consciousness is not a product of the universe, but a fundamental part of it? This view, known as panpsychism, suggests that consciousness is a basic property of reality, akin to mass or charge. It doesn't emerge at a certain level of complexity. It is instead inherent in all matter to varying degrees. In this view, an electron might possess a minuscule, simple form of experience, a proto-consciousness. While this might sound strange, it offers an elegant solution to the hard problem. Consciousness didn't emerge from non-conscious stuff. It was always there, and complex brains didn't create it but rather amplified it, channeling it into the rich, detailed experience we enjoy. An even more cosmic extension of this idea is cosmopsychism, which proposes that consciousness is not bottom-up from particles, but top-down from the cosmos itself. This theory suggests the universe as a whole may possess a unified, fundamental consciousness, and our individual minds are not separate entities but rather localized expressions of this universal mind, much like whirlpools are temporary patterns within a larger river. This doesn't imply a personal, thinking God, but rather a fundamental, conscious field that is as integral to the cosmos as the gravitational field. If true, this would mean that the universe is not a cold, empty machine but is, in its very essence, awake and aware, and we are literally pieces of the universe becoming aware of itself. This transforms our search for a hidden architecture from a purely physical endeavor into something much deeper. If consciousness is fundamental, then the cosmic architecture we've been tracing, the fine-tuned constants, the mathematical laws, the holographic principles, might not just be a set of blind rules for generating structure. They could be the conditions necessary for facilitating and amplifying conscious experience. The universe is structured in this specific way, not just to allow for galaxies and stars, but to allow for galaxies and stars that can give rise to beings capable of wonder, love, and curiosity. The architecture is designed not merely for existence, but for witnessed existence. This provides a powerful, potential answer to the Anthropic Principle. The universe is tuned for life because life, and the consciousness it brings, is a fundamental aspect of its purpose. This clue connects the grandest scales of the cosmos directly to the most personal scale of our being. It suggests that in our quest to understand the hidden architecture of the universe, we are not just external observers analyzing a separate system. We are that system looking inward. Our own consciousness is not a fluke in a meaningless void. It is a feature of the cosmic landscape, a vital component of the very reality we are trying to decode. The mystery of why there is something rather than nothing is inextricably linked to the mystery of why it feels like something to be here. In seeking to understand the architecture of the cosmos, we may ultimately be seeking to understand the deepest nature of ourselves. Look around you, the screen you're reading this on, the air you're breathing, the very blood pumping through your veins, all of it is made of elements forged in the hearts of distant, long-dead stars. This isn't just a poetic metaphor, it is the literal story of our cosmic origins, and it reveals a hidden architecture operating with breathtaking precision on both the grandest and the smallest of scales. This process, known as stellar nucleosynthesis, is not a chaotic, random event. It is a meticulously orchestrated cosmic factory, running on a set of physical laws so exact that they reliably produce the entire periodic table of elements, the very building blocks of reality itself. The magic begins with the universe's simplest and most abundant element, hydrogen, a single proton orbited by a single electron. Under the immense gravitational pressure in the core of a star, hydrogen atoms are squeezed together or fused to form helium. This process releases a tremendous amount of energy which we see as starlight, and it's the fundamental engine that powers every star in the sky. But the story doesn't end there. For a star like our Sun, helium is the final product, But for more massive stars, the factory floor has many more levels. Once the hydrogen fuel is depleted, the star's core contracts, heating up even further until it becomes hot enough to begin fusing helium atoms into carbon. Then, in a cascading series of life cycles, carbon can be fused into oxygen, neon, and magnesium, and so on, climbing up the periodic table step by step. The most dramatic and creative phase of this cosmic production occurs in the final, violent death throes of the most massive stars, a supernova explosion. In the unimaginable heat and pressure of this stellar detonation, elements are forged through processes that simply cannot happen anywhere else. This is where the iron in your blood, the calcium in your bones, and the gold in a wedding ring are created. In a matter of seconds, a supernova can produce elements all the way up to uranium, scattering them across the interstellar medium like a cosmic gardener sowing seeds for future generations. These enriched clouds of gas and dust later collapse to form new stars, planets, and eventually, living beings capable of pondering their own stellar ancestry. This is a cycle of cosmic recycling on an epic scale, a process written into the laws of physics that ensures the universe can become more complex over time. But the true clue to a hidden architecture lies not just in the process, but in the stunningly specific products it creates. The periodic table is not a random list of elements. It is a profound reflection of deep underlying symmetries in the laws of quantum mechanics. The table's structure, its periods and groups, directly mirrors the arrangement of electrons orbiting an atomic nucleus, which is itself governed by the fundamental rules of quantum physics. The fact that elements with similar properties fall into neat columns is not a coincidence. It is a direct consequence of the mathematical structure of reality. The periodic table is a map, and the territory it describes is the quantum architecture of matter itself. Perhaps the most compelling evidence for a cosmos that encourages complexity is the incredible abundance of the very elements that are essential for life as we know it. Carbon, oxygen, nitrogen, and phosphorus are not rare cosmic oddities. They are among the most common elements in the universe. This is not an accident of stellar physics. The nuclear processes that create these elements are themselves fine-tuned. For instance, the process that creates carbon inside stars relies on a breathtakingly precise resonance between energy levels in the carbon nucleus and the particles that form it. If this resonance were even slightly different, carbon would be extremely rare, and the universe would be devoid of the complex chemistry necessary for life. Similarly, the elements necessary for water, for metabolic reactions, and for genetic material are all produced in abundance by the standard life cycles of stars. It is as if the universe's architectural blueprint explicitly includes not just the possibility of life, but a clear and efficient pathway for its eventual emergence. The stars are not just furnaces, they are alchemists following a precise and elegant recipe to transform the simple primordial hydrogen from the Big Bang into the rich chemical tapestry that makes our existence possible. For all the universe's apparent hospitality, with its trillions of planets orbiting within the habitable zones of stable stars, the cosmos presents us with a profound and unsettling silence. This quiet is the heart of the Fermi Paradox, named for physicist Enrico Fermi, who famously asked, "Where is everybody?" Given the staggering number of stars and the high probability of Earth-like worlds, the galaxy should be teeming with life, its channels buzzing with communication. Our radio telescopes, however, have heard nothing but the natural static of the cosmos. This great silence is not just a puzzle. It is a powerful clue that the universe's architecture might include features we have not yet imagined, features that could either preserve life in sacred isolation or render it astonishingly rare. One compelling resolution to this paradox is that the conditions for a civilization to arise and persist are not just a matter of being in the right place at the right time. They may require a series of evolutionary and technological hurdles so specific and so difficult to overcome that they act as a great filter. This filter could be a single, nearly impassable barrier that prevents life from progressing to a spacefaring stage. Perhaps the emergence of self-replicating molecules from non-living chemistry is itself a cosmic fluke of unimaginable rarity. Or maybe the jump from single-celled to complex, multicellular life is the monumental bottleneck. If the filter lies in our past, we are the beneficiaries of a cosmic lottery win of epic proportions, and the silence makes sense because we are truly alone. A more ominous possibility is that the great filter lies in our future. This suggests that the development of advanced technology inevitably leads to a civilization's self-destruction, whether through nuclear war, environmental collapse, or a runaway artificial intelligence. In this grim scenario, the galaxy might be littered with the fossils of civilizations that briefly flickered into existence before snuffing themselves out. The silence, then, is not a sign of our uniqueness but a somber warning, a cosmic graveyard suggesting that the architectural plan for intelligent life includes a built-in expiration date. But there is another, far more intriguing possibility. What if the silence is not a sign of absence or failure, but a feature of the design itself? This idea, sometimes called the zoo hypothesis or the planetarium hypothesis, suggests that the universe is intentionally structured to separate emerging civilizations. Advanced intelligences, or the laws of nature itself, might have established a principle of non-interference, a cosmic prime directive designed to allow young species like ours to develop naturally, free from outside influence or contamination. The vast distances between stars, the limitations of the speed of light, and the sheer immensity of the universe itself could be part of this architectural isolation, creating natural quarantine zones where life can safely evolve. This perspective transforms the Fermi Paradox from a question of scarcity into one of purpose. The fine-tuning we observe, the precise constants that allow for chemistry and long-lived stars might not just be for life in general, but for independent life. The architecture could be designed to cultivate uniqueness and diversity, ensuring that each civilization that arises does so from its own unique evolutionary path, developing its own culture, philosophy, and understanding of the universe. The silence is not an empty void but a protected space, a nursery for consciousness. We are not alone because no one is out there. We are alone because the cosmos is architected to give us the room to grow up on our own, to one day perhaps join a galactic community as a mature and independent species, rather than being discovered as a primitive curiosity. This profound notion suggests that the hidden architecture is not just a set of physical laws, but a framework with a deep, perhaps even ethical, intentionality. And then there are the numbers that seem to whisper to us from the edges of reality, the cosmic coincidences that feel too striking to ignore. Consider the total number of atoms in the entire observable universe, a figure estimated to be around 10 to the power of 80. Now consider the total number of possible unique games of chess. That number, known as the Shannon number after the father of information theory, is calculated to be roughly 10 to the power of 120. The sheer scale of these two numbers, both hovering around these immense powers of 10, is enough to give anyone pause. It's as if the complexity of the entire physical cosmos is somehow mirrored in the abstract complexity of a simple game, a hint that information and matter might be two sides of the same coin. These numerical echoes don't stop there. Look at the ratio of the strength of the electromagnetic force to the force of gravity. it is an astronomically large number, around 10 to the power of 36. Now consider the approximate age of the universe, about 13.8 billion years, expressed in terms of the smallest possible units of time, the Planck time. That number comes out to roughly 10 to the power of 60. The square root of that number, it's about 10 to the power of 30, a figure that is intriguingly close to that earlier ratio of forces. This could be a complete fluke, a random alignment of digits with no deeper meaning. Or it could be a subtle clue that the fundamental forces of nature are somehow synchronized with the very age of the cosmos, that the universe's expansion and its internal laws are part of a single, coordinated design. Perhaps the most famous of these numerical curiosities is the work of physicist Arthur Eddington, who in the early 20th century became fascinated with certain fundamental constants. He notably calculated a precise value for the inverse of the fine structure constant, a dimensionless number that governs the strength of electromagnetic interactions. His calculated value was 137, and he devoted years to developing intricate numerical arguments for why this number had to be an integer. While modern, more precise measurements have shown the constant to be approximately 137.036, making it not a whole number, Eddington's pursuit highlights a deep human intuition that the universe's parameters should not be random decimals, but should reflect a deeper, more elegant mathematical order. The prevalence of certain mathematical constants only deepens the mystery. We find the number pi, the ratio of a circle's circumference to its diameter, appearing in equations that describe the fundamental principles of the universe, from the shape of an electron's orbit to the curvature of spacetime itself. The number e, the base of the natural logarithm, is woven into the fabric of reality, governing rates of growth and decay in everything from nuclear radiation to population biology. Their ubiquitous presence suggests they are not merely human inventions for calculation, but are fundamental features of the cosmic landscape, pre-existing constants waiting to be discovered. So, how should we approach these tantalizing numerical patterns? The scientific mainstream often dismisses them as apophenia, the human tendency to find meaningful patterns in random noise. They argue that in a universe of immense numbers, some coincidences are statistically inevitable, and investing them with significance is a form of modern numerology, a search for magic in a mechanistic world. This is a healthy skepticism, a necessary guard against finding patterns where none exist. But a more open-minded perspective suggests that we should not be so quick to dismiss every correlation. Throughout the history of science, some of our greatest breakthroughs began with a scientist staring at a strange coincidence and refusing to look away. The structure of the benzene ring came to Auguste Kekulé in a dream of a snake eating its own tail. The periodic table was initially organized by Dmitri Mendeleev based on patterns in atomic weights, which later revealed the deeper reality of atomic numbers. These leaps started not with strict deduction, but with a hunch, a pattern, a coincidence that hinted at a deeper truth. The cosmic coincidences we find may be the universe's way of dropping hints, subtle clues written in the language of mathematics that point toward a unified architecture. They encourage us to look beyond the stark separation between fundamental forces and the evolution of the cosmos, between the very large and the very small. These numerical resonances suggest that everything is connected, that the constants that govern the interactions of atoms are intimately tied to the universe's age, size, and structure. They invite us to consider that the cosmos might be a coherent, integrated whole, and that by paying attention to these numerical whispers, we might one day hear the full story it is trying to tell. But what if the true nature of reality is even more fantastical than we have yet imagined? a cosmos not of point-like particles but of tiny, vibrating loops of energy. This is the audacious proposal of string theory, a framework that compels us to consider our 22nd clue, the existence of extra dimensions of space, curled up into a geometry so minute that it has eluded all detection, yet potentially holding the key to the universe's deepest architectural secrets. For centuries, we have operated under the assumption that our universe has 3 dimensions of space and 1 of time. But what if this is merely our limited, large-scale perspective? String theory suggests that at the most fundamental level, the universe is not composed of 0-dimensional points, but of 1-dimensional strings, unimaginably small filaments of energy whose different modes of vibration give rise to the entire menagerie of particles we observe. An electron is not a dot, it is a string vibrating at one specific frequency. A photon is the same type of string, just vibrating differently. The mathematics of these vibrating strings, however, only works consistently if the universe has more than just 3 spatial dimensions. To avoid logical contradictions and to naturally include the force of gravity within its quantum description, string theory requires a total of 10 dimensions. This immediately presents a puzzle. If there are extra dimensions, where are they? The theory's elegant solution is that 6 of these dimensions are compactified, or curled up into a fantastically complex, tiny shape at every single point in space. To understand this, imagine a long, thin garden hose stretching off into the distance. From a great distance, it appears to be a simple one-dimensional line. But if an ant were to crawl onto it, it would discover a second dimension, the circular dimension wrapped around the hose's circumference. In an analogous way, our 3-dimensional space might be like the length of the hose, while 6 extra dimensions are curled up into a shape at every point, a shape far more complex than a simple circle, known to mathematicians as a Calabi-Yau manifold. This is where the theory connects directly to the idea of a cosmic architecture. The specific way these extra dimensions are folded and curled is not arbitrary. Their exact geometry determines the laws of physics in our observable 3-dimensional world. The shape of these hidden dimensions would dictate the masses of elementary particles, the number of particle families, and the strengths of the fundamental forces. In this breathtaking vision, the properties of every electron and every quark, the very constants we've marveled at for being so finely tuned, are not arbitrary numbers input into the universe's source code. They are the inevitable consequence of geometry. The universe is fine-tuned because the geometry of these hidden dimensions is fixed, and that geometry produces the specific physical laws we measure. The architecture is not just hidden, it is multidimensional, a complex geometric form whose topology writes the rules of reality. The ultimate ambition of string theory is to be a theory of everything, a single, unified framework from which all the forces of nature, gravity, electromagnetism, and the nuclear forces naturally emerge. It represents the pinnacle of the search for a hidden architecture, a mathematical structure so profound and self-contained that it could describe every phenomenon from the Big Bang to the bonding of atoms. Yet, for all its mathematical beauty and promise, string theory remains just that, a theory. Its predictions currently operate at energy scales far beyond the reach of any particle accelerator we could hope to build, and the specific Calabi-Yau shape that describes our universe is just one of a staggering number of possibilities, perhaps as many as 10 to the 500. This vast landscape of potential solutions presents a formidable challenge, making experimental verification incredibly difficult. The search for evidence, therefore, becomes an exercise in indirect detective work. Physicists are creatively looking for any faint signature that might betray the presence of these extra dimensions. Some theories suggest that gravity, which feels so weak compared to the other forces, might actually be as strong as they are, but its strength is diluted as it leaks into these extra, curled-up dimensions. If this is true, experiments looking for deviations from Newton's law of gravity at incredibly small, sub-millimeter distances could potentially find a telltale sign. Others have proposed that the massive energies involved in the earliest moments of the Big Bang might have caused these extra dimensions to briefly unfurl, leaving an imprint on the cosmic microwave background or in the gravitational waves that ripple through the fabric of spacetime, a cosmic fossil waiting to be discovered. The pursuit of string theory, even without direct proof, is a powerful driver of mathematical innovation and conceptual revolution, forcing us to expand our imagination of what the universe's ultimate blueprint might look like and compelling us to keep searching for the subtle architectural details hidden in the geometry of everything. So let's take a step back and look at the entire mosaic we've assembled. Individually, each of these 22 clues is a fascinating puzzle piece, a strange anomaly, a precise calibration, or a deep mystery that challenges our conventional understanding. But when we bring them all together and view them as a whole, a breathtaking image begins to resolve. This isn't a collection of unrelated curiosities. It's a coherent portrait of a universe that is fundamentally structured, ordered, and perhaps even designed. The fine-tuning of constants, the invisible scaffolding of dark matter, the mathematical elegance of physical laws, the holographic encoding of information, and the profound mystery of consciousness, they aren't separate threads. They are different colored strands woven together into a single, magnificent tapestry, all pointing toward the existence of a hidden cosmic architecture. This architecture appears to operate on multiple, interconnected levels. On one level, it is profoundly mathematical. The universe doesn't just use math as a tool, it seems to be composed of it. The constants are numerical values, the laws are equations, and the behavior of everything from quarks to quasars follows a logical, computable pattern. This suggests a reality whose blueprints are drawn not in ink, but in numbers and geometric forms. On another level, this architecture is deeply informational. The holographic principle and the behavior of black holes hint that the fundamental stuff of reality might not be matter or energy, but bits of information. The universe could be a cosmic computation, a dynamic process where the laws of physics are the algorithms running on the hardware of spacetime. Particles and forces would then be the output of this computation, the user interface of a reality whose source code is written in data. Perhaps the most profound implication of this synthesis is the possibility that this architecture is not just a blind, automatic system, but something with a direction, or even an intention. The Anthropic Principle and the fine-tuning for life suggest that the universe's parameters were set not just for stability, but for the specific purpose of generating complexity and, ultimately, consciousness. The universe seems to have properties that not only allow for observers but that actively encourage their emergence. This doesn't necessarily point to a traditional, personal deity, but it does strongly suggest a cosmos with a built-in bias toward life and mind. We are not accidental tourists in a meaningless void. We may be an integral part of the universe's function, the means by which it comes to know and understand itself. This grand synthesis doesn't mark the end of science, it illuminates its next great frontier. The task ahead is to move from recognizing this architecture to truly understanding it. This will require a bold blending of disciplines. Physics must dance with philosophy. Cosmology must converse with metaphysics. We need to develop new languages and new concepts to describe a reality that is more strange and wonderful than we ever imagined. The questions we are asking now are among the most profound humanity has ever contemplated. Are we living in a mathematical universe? Is consciousness a fundamental feature of reality? Does the cosmos have a purpose? This journey of discovery is not just about collecting more data. It's about expanding the very framework of thought itself, inviting us to approach the cosmos not just with instruments, but with humility, curiosity, and a sense of awe. We've journeyed together through 22 remarkable clues, each one a thread in a vast and intricate tapestry that suggests our universe is far more than a chaotic accident. From the impossibly precise fine-tuning of physical constants to the silent, shaping hands of dark matter and dark energy, from the mathematical elegance underpinning reality to the profound mystery of our own consciousness, a compelling narrative emerges. This isn't a story of isolated curiosities, but a converging picture of a cosmos built upon a deep, hidden architecture, a framework of breathtaking order and perhaps even intention. What does this mean for us right here, right now? It means that every time we look up at the night sky, we are not just looking into a random scattering of lights. We are gazing at the outermost expression of a magnificent, structured design, a cosmic blueprint that we are only just beginning to decipher. This understanding transforms our place in the universe from accidental tourists to active participants in a grand, ongoing discovery. The curiosity that drives you to watch videos like this, the awe you feel when contemplating the scale of it all, is not an aside to the human experience. It may be a central part of why this cosmic architecture exists in the first place. The search for this underlying order is one of the greatest adventures of the human spirit. It's a quest that connects the largest questions of cosmology to the most intimate questions of our own existence. And this journey is far from over. With every new telescope peering deeper into space, every particle detector buried underground, and every theoretical breakthrough that challenges our assumptions, we gather another piece of the puzzle. We are living in a golden age of exploration, not just of outer space, but of the very nature of reality itself. I am incredibly curious to know which of these clues resonated most deeply with you. Was it the spooky connectedness of quantum entanglement that stretched your mind, or the silent power of dark matter holding the cosmos together? Did the mathematical nature of reality strike a chord, or did the mystery of consciousness feel like the most personal and profound clue of all? Share your thoughts in the comments below. Let's continue this conversation and learn from each other's perspectives. If this exploration sparked your sense of wonder, make sure you don't miss the next one. Liking this video helps others discover these ideas. Subscribing tells YouTube you want more content like this. And hitting that notification bell ensures you'll be the first to know when we release our next deep dive into the mysteries of the universe. From the bottom of my heart, thank you for dedicating your time and your curiosity to this journey. Never stop asking questions, never stop seeking answers, and always remember to look up and wonder.